Tonight, we're exploring one of astronomy's most peculiar choices. A unit called the Parsec that almost no star actually sits at, yet it appears in every professional research paper about the cosmos. By the end, you'll understand not just what it is, but the fascinating story of how a measurement choice made in 1838 still dominates astronomy today. If you enjoy these explorations, a like or subscribe helps. Now let's begin. Imagine you're an astronomer in 1837. You stand at your telescope night after night, staring at a faint star called 61 Cygni. You know Earth is moving through space, orbiting the Sun at tremendous speed. You know that if you're patient enough, precise enough, careful enough, you might detect the star's position shift ever so slightly against the background of more distant stars. And if you can measure that shift, you'll accomplish something humans have been trying to do for 2,000 years. You'll measure the distance to a star. Friedrich Wilhelm Bessel did exactly that. What he couldn't have known was that his measurement would create a unit of distance that would still dominate astronomy nearly 2 centuries later. A unit that makes no intuitive sense to anyone outside the field. A unit that marks no natural boundary in space. A unit based purely on the geometry of his measurement technique, the parsec. For most of human history, stellar distances were a complete mystery. Ancient Greek astronomer Hipparchus, around 130 BCE, catalogued over 1,000 stars. He measured their positions carefully, tracked their movements across the sky, recorded their brightness. But distance? He had no idea. His best guess was that they sat on a crystal sphere beyond the planets, all equally far from Earth. This wasn't stupidity or lack of imagination. It was the best explanation fitting available observations. The stars appeared to be fixed points of light that never moved relative to each other. They kept perfect formation night after night, year after year, century after century. The ancient Greeks actually had a word for this celestial sphere. They called it the firmament, from the Latin word meaning to make firm or strengthen. The idea was that the stars were literally embedded in a solid crystalline sphere that rotated around Earth once per day. This sphere sat beyond the planets, which the Greeks knew moved against the stellar background. They had tracked Mars, Jupiter, and Saturn carefully and watched these wandering stars trace complex paths through the constellations. But the stars themselves never budged relative to each other. Aristotle, writing in the 4th century BCE, argued that this celestial sphere must be made of a 5th element, different from the earth, water, air, and fire found below the moon. He called it ether, or quintessence. This substance was perfect, unchanging, and eternal. The stars embedded in this sphere partook of its perfection. They never changed brightness, never appeared or disappeared, never moved except for their daily rotation with the sphere itself. This model made sense for 2,000 years because nobody had instruments capable of detecting stellar parallax or proper motion. The stars really did appear absolutely fixed. Every observation confirmed the model. When Ptolemy compiled his great star catalogue around 150 CE, documenting over 1,000 stars and their positions, he found the same patterns Hipparchus had seen 3 centuries earlier. The constellations hadn't changed shape at all. For 2 millennia, nobody did better. The technology simply didn't exist. Telescopes were eventually invented in the 1600s, and they revealed astonishing details about the moon, planets, and stars. Galileo saw mountains on the moon and 4 moons orbiting Jupiter. He discovered that the Milky Way consisted of countless individual stars, but he still couldn't answer the fundamental question of how far away anything was. The stars appeared absolutely fixed. If something doesn't move, you can't triangulate its distance. You need to view an object from two different positions and measure how its position changes. That's how your brain perceives depth. Your two eyes see slightly different views of the world, and your brain uses that difference to judge distance. Close one eye and reach out to touch something. It's harder because you've lost that depth perception. Your brain needs the parallax between your two eyes. For stars, we needed something similar, but on a cosmic scale. Human eyes are separated by only about 6 centimeters. That's enough to give depth perception for objects a few meters away, but utterly useless for anything at astronomical distances. We needed a much larger baseline. By the 1600s, scientists had figured out a clever idea. Use Earth's orbit around the Sun as your triangulation baseline. Johannes Kepler had established that Earth orbits the Sun in a roughly circular path. By the mid-1600s, astronomers had measured Earth's orbital size fairly accurately by observing transits of Venus across the Sun's face. They knew Earth orbits in a path about 300 million kilometers in diameter. That's 186 million miles. This means that in January, Earth is on one side of the Sun, and 6 months later in July, Earth is on the complete opposite side. Observe a star in January. Note its exact position against the background of more distant stars. Then observe the same star in July from the opposite side of the orbit. You're viewing from two positions separated by that full diameter. It's like having eyes separated by 300 million kilometers instead of 6 centimeters. Even the nearest stars should show a tiny shift against the more distant background stars. This shift is called stellar parallax. Measure this shift, use basic trigonometry, and you can calculate the distance. The concept is beautifully simple. Draw a triangle. The base is Earth's orbit diameter. The vertex is the star. Measure the angle at the star, and you can calculate how far away it is. Simple geometry that any student learns in school. The execution, however, proved nearly impossible. The problem was that the shift is incredibly tiny. We're talking about angles smaller than 1 arcsecond. To understand how small 1 arcsecond is, imagine dividing a degree into 60 parts. Each part is 1 arcminute. Now divide each arcminute into 60 more parts. Each of those is 1 arcsecond. So 1 arcsecond is 1/3600th of a degree. To give you a physical sense of this, if you hold a tennis ball at the distance of 1 kilometer, the ball appears about 1 arcsecond wide. If you're standing on a beach and you see a ship on the horizon 10 kilometers away, a person standing on that ship's deck appears about 1 arcsecond tall. That's the kind of precision 17th century telescopes would need to detect stellar parallax. They couldn't do it. The best telescopes of the time had mechanical wobbles larger than the signal astronomers were trying to detect. Atmospheric turbulence blurred images by several arcseconds. Temperature changes made telescope parts expand and contract by amounts that threw off alignment. Even the astronomer's own heartbeat could introduce vibrations large enough to ruin measurements. The foundations of observatory buildings settled and shifted with temperature. Wind pushed on telescope tubes. Robert Hooke tried in 1669. He was a brilliant scientist, one of England's leading experimentalists. Hooke had contributed to optics, mechanics, astronomy, and biology. He coined the word cell after seeing the structure of cork under a microscope. He formulated Hooke's law of elasticity. He was a serious scientist tackling a serious problem. Hooke built a special telescope mounted in a tall building to minimize atmospheric distortion. The idea was that mounting the telescope high up would put it above some of the turbulent air near the ground. He observed a bright star called Gamma Draconis for months, took careful measurements, detected what he thought was a shift in position. He published his findings, claiming to have measured stellar parallax at last. He was wrong. What he had actually detected was something called stellar aberration, a different effect entirely that comes from the combination of light's finite speed and Earth's motion through space. Here's how aberration works. Light travels at finite speed, about 300,000 kilometers per second. Earth is moving around the Sun at about 30 kilometers per second. When you point a telescope at a star, you have to tilt it slightly in the direction of Earth's motion to compensate for the fact that light is traveling down the tube while Earth is moving sideways. It's like running through rain. Even if the rain is falling straight down, you have to tilt your umbrella forward because you're moving horizontally. This aberration effect is real and measurable. But it's not parallax. Parallax makes nearby stars shift against distant background stars. Aberration makes all stars shift in the same direction by the same amount. Hooke had discovered something real and interesting, just not what he thought he'd discovered. The actual discovery of aberration is credited to James Bradley in 1728, who figured out what was really happening. William Herschel tried a different approach. Herschel was the astronomer who discovered Uranus in 1781, the first planet discovered in recorded history. Before Uranus, humanity knew 5 planets, Mercury through Saturn, all visible to the naked eye and known since ancient times. Herschel's discovery of a 6th planet made him instantly famous. He reasoned that if you observe double stars, pairs of stars that appear close together in the sky, one star in the pair might be much nearer to Earth than its companion. If so, the near star should show parallax, while the distant one doesn't. Over many years, he made thousands of painstaking measurements of double star systems, carefully tracking the angular separation between the components of each pair. He never found parallax. But his work wasn't wasted. He discovered that many double stars aren't just chance alignments, 2 unrelated stars that happen to lie along the same line of sight from Earth. They actually orbit each other gravitationally. He had discovered binary star systems, pairs of stars bound together by gravity, orbiting their common center of mass. This turned out to be one of astronomy's most important discoveries. Binary stars became crucial tools for measuring stellar masses. By watching how fast 2 stars orbit each other and measuring their separation, you can calculate their masses using Newton's laws. This is still how we measure most stellar masses today. Herschel's failed attempt to find parallax led to a discovery that transformed stellar astronomy. By the early 1800s, measuring stellar parallax had become astronomy's great challenge. It was the Holy Grail. Everyone knew it should be possible in principle, but nobody could actually do it. The failure wasn't from lack of trying. Dozens of skilled astronomers across Europe spent years on the problem. Some claimed success, publishing measurements that other astronomers couldn't replicate. The claimed distances varied wildly, suggesting the measurements weren't reliable. The distances were too great, and the measurement too difficult for the instruments of the time. Friedrich Wilhelm Bessel was different from his predecessors. He was German, born in 1784 in the town of Minden in Westphalia. Interestingly, Bessel didn't start out as an astronomer. He began his career as an accountant for a trading company. But he taught himself mathematics and astronomy in his spare time. He was particularly interested in navigation and studied how to calculate positions using astronomical observations. At age 20, Bessel calculated the orbit of Halley's Comet using old observations. He did this purely as a hobby, but his work was so good that a professional astronomer, Heinrich Olbers, noticed it and helped Bessel get a position as an assistant at a small observatory. By age 26, Bessel was appointed director of a new observatory being built in Königsberg. He would spend the rest of his career there, making it one of Europe's leading observatories through the quality of his work. Bessel became one of the most meticulous scientists of his generation. He was obsessed with precision and error analysis. This was still a time when many scientists took measurements somewhat casually, writing down whatever their instruments showed without carefully considering all the sources of error. Bessel was different. He didn't just take measurements. He analyzed every possible source of error, built mathematical models to account for them, and repeated observations until he was absolutely certain of his results. He studied how atmospheric refraction changed with temperature and humidity. Air acts like a lens, bending light that passes through it. The amount of bending depends on air density, which varies with temperature, pressure, and water vapor content. Bessel made extensive measurements of these effects and developed correction formulas. He measured how his telescope's metal parts expanded and contracted with even small temperature changes. A brass tube might expand by a millimeter or more with a 10-degree temperature change. That sounds small, but it's enough to throw off the precise angular measurements needed for parallax. Bessel attached thermometers to his telescope and measured its length at different temperatures, developing correction factors. He tracked the mechanical play in his mount, the wobbles in his building's foundation, even the effect of wind pressure on the observatory dome. Every possible source of error was studied, measured, and accounted for. This level of care was unusual for the time, and is exactly what was needed to detect parallax. In 1837, Bessel decided to tackle the parallax problem directly. He chose his target carefully. He picked a star called 61 Cygni, located in the constellation Cygnus the Swan. It wasn't particularly bright. In fact, you need a small telescope to see it clearly. Under dark skies with good vision, you might barely glimpse it, but most people would miss it entirely. It's what astronomers call a fifth magnitude star, at the limit of naked eye visibility. But 61 Cygni had one crucial property that suggested it might be relatively close to Earth. It moved across the sky faster than almost any other star. This motion isn't parallax. It's called proper motion, the star's actual movement through space over time. Most stars have such small proper motions that they appear fixed even over human lifetimes. The constellations look the same now as they did to ancient astronomers, but a few nearby stars have measurable proper motion. Bessel reasoned that a star with high proper motion was probably relatively nearby. Think about watching cars on a highway from an overpass. The cars on the near lanes seem to zoom past, while distant cars barely seem to move. Same principle applies in space. Nearby stars moving at typical stellar velocities show larger proper motions than distant stars moving at the same speed. 61 Cygni has one of the largest proper motions known at the time, suggesting it was a nearby star and therefore a good parallax target. From August 1837 through August 1838, Bessel made hundreds of observations using a specialized instrument called a heliometer. A heliometer is essentially a telescope with a split objective lens. The front lens of the telescope is cut in half, and one half can be slid sideways relative to the other. This creates two images of whatever you're looking at. By adjusting how much you slide the lens, you can superimpose the two images or separate them by precise amounts. This design lets you measure tiny angles with remarkable precision. If you're measuring the separation between two stars, you can put one star image from the left lens onto the other star image from the right lens and read off the separation from how far you had to slide the lens. Bessel's heliometer could measure angles down to about 1/10 of an arcsecond under good conditions. This was cutting-edge precision for 1837. But Bessel didn't just point his telescope at 61 Cygni and measure its position. That wouldn't work because he'd have no reference frame. The telescope itself might shift position slightly, or the whole building might settle. You need reference points. Instead, Bessel observed multiple reference stars in the same field of view. These were stars chosen to be so distant that their parallax would be essentially unmeasurable, effectively at infinite distance. Every clear night, weather permitting, Bessel measured the angular separation between 61 Cygni and these reference stars. He would measure the distance from 61 Cygni to reference star A, then to reference star B, then to reference star C. Multiple measurements, multiple references, all to maximize accuracy and catch any systematic errors. Over the course of months, as Earth moved around its orbit, 61 Cygni traced out a tiny ellipse against the background of reference stars. In January, Earth was on one side of its orbit, and 61 Cygni appeared slightly shifted in one direction. In April, Earth had moved a quarter of the way around its orbit, and 61 Cygni appeared shifted differently. In July, Earth was on the opposite side of the orbit, and the shift reversed. By October, the cycle continued. The size of that ellipse directly gave the parallax. But extracting that signal required dealing with a host of complicating factors, each much larger than the effect Bessel was trying to measure. Atmospheric refraction bends starlight, and the amount of bending changes with the star's altitude above the horizon, the air temperature, the humidity, even the barometric pressure. A star near the horizon might appear displaced by half an arcminute or more. That's 30 arcseconds, about 100 times larger than the parallax Bessel was measuring. He had to measure or calculate all these effects and subtract them out. The telescope's metal parts expanded when warm and contracted when cold. Even a change of a few degrees could shift the telescope's alignment by amounts larger than the parallax signal. The mount had tiny amounts of mechanical play that changed depending on which direction the telescope pointed. Point the telescope east and gravity pulls on the tube one way. Point it west and gravity pulls differently, causing small flexures. Earth's axis precesses, like a wobbling top, causing all stellar positions to drift slowly over time. This is a tiny effect over 1 year, but Bessel had to account for it. Then there's aberration. The effect Hooke had mistakenly identified as parallax a century and a half earlier. Aberration makes stars appear shifted in the direction of Earth's motion by about 20 arcseconds, and it's much larger than parallax. Bessel had to calculate and remove the aberration effect from every measurement. He observed at different times of night to see how changing altitude affected measurements. Higher in the sky, less atmosphere to look through, less refraction to account for. He recorded air temperature for every observation. He measured barometric pressure. He even noted wind conditions because wind can shake the telescope and building. He measured the expansion and contraction of his telescope with thermometers attached to the metal tube. He developed mathematical formulas relating temperature to telescope length. He built models of mechanical flexure. Every error source got its own mathematical treatment. Only after accounting for everything else, after months of painstaking analysis, could he isolate the tiny parallax signal buried in the noise. His result was 0.3136 arcseconds of parallax. To appreciate how small this is, imagine you're looking at a dime held at arm's length, about 60 centimeters away. The width of that dime, as seen from your eye, is an angle of about 20,000 times larger than the parallax Bessel measured. He was measuring an angle approximately equal to the width of a human hair seen from 100 meters away, or the angle subtended by the period at the end of this sentence seen from across a football field. From this measurement, using basic trigonometry, Bessel calculated that 61 Cygni was about 10.3 light-years away. That's roughly 97 trillion kilometers. To put this in perspective, if you could somehow drive to 61 Cygni at highway speed, say 100 kilometers per hour, the trip would take about 110 million years. Modern measurements with better instruments give 11.4 light-years, so Bessel was remarkably close. His measurement was accurate to within about 10%, extraordinary for 1838. This was extraordinary work. 13 months of nearly continuous observations. Bessel had to observe on every clear night, which in northern Germany means dealing with clouds, rain, and short winter days. He made hundreds of individual measurements, then months of mathematical analysis, careful consideration of every possible error source. Calculations done entirely by hand, using logarithm tables, because electronic calculators wouldn't exist for another century. It's precisely why nobody had succeeded before. The level of precision required was far beyond what seemed possible with 1838 technology. The measurement was at the very edge of what was physically achievable with the best instruments and techniques available. But Bessel managed it through pure, obsessive attention to detail, mathematical skill, and relentless patience. Within months of Bessel's announcement in late 1838, the floodgates opened. Thomas Henderson, a Scottish astronomer working at the Royal Observatory in Cape Town, South Africa, published parallax measurements for Alpha Centauri. Interestingly, Henderson had actually made his observations before Bessel, starting back in 1832. He had measured Alpha Centauri's position carefully over many months. But Henderson was cautious, perhaps too cautious. He saw a shift in position that looked like parallax, but he wasn't completely confident in his results. He worried about systematic errors. He questioned whether his instruments were accurate enough. So he sat on his data, continuing to analyze it, hesitating to publish. When Bessel's announcement came through in early 1839, Henderson realized his own measurements were valid and rushed to publish. His data was actually better than Bessel's in some ways because Alpha Centauri is brighter and closer, making the parallax larger and easier to measure. Alpha Centauri turned out to be even closer than 61 Cygni, at about 4.4 light-years. This is interesting from a history of science perspective. Henderson actually made the first stellar parallax measurements, but Bessel gets credit for the discovery because Bessel published first. This happens sometimes in science. The person who publishes first gets the credit, even if someone else did the work earlier. It's why scientists often rush to publish as soon as they have solid results. Friedrich Georg Wilhelm von Struve, working at the Dorpat Observatory in what's now Tartu, Estonia, measured Vega's parallax shortly after Bessel's and Henderson's announcements. Struve was another meticulous observer who had been working on the parallax problem for years. Vega is much farther than the other two stars, at about 25 light-years, making its parallax even tinier and harder to measure. Struve's measurement was less accurate than Bessel's or Henderson's, but it was still a genuine detection. Suddenly, after 2,000 years of complete mystery about stellar distances, we had distances to 3 stars, and more were coming. Astronomers worldwide began parallax programs. Within a few years, distances to dozens of stars had been measured. By the early 1900s, hundreds of stars had measured parallaxes. By the mid-20th century, thousands. Each measurement confirmed that stars were scattered at enormous distances, far beyond anything in the solar system. The nearest star, Alpha Centauri, was 40 trillion kilometers away. That's about 270,000 times farther than the Sun. Sirius, one of the brightest stars in our sky, and fairly close by stellar standards, was 81 trillion kilometers away. More distant stars were even farther. This discovery fundamentally changed humanity's understanding of the universe's scale. Before parallax measurements, some astronomers thought the Milky Way might be only a few thousand astronomical units across, perhaps 100 times the size of the solar system. After Bessel's work, it became clear the galaxy was millions of times larger. The Sun wasn't at the center of a small stellar system. It was one ordinary star among countless others scattered across distances so vast they were hard to comprehend. Our sense of cosmic scale expanded enormously. The universe went from being a solar system, plus a sphere of stars just beyond the planets, to being a vast space containing objects at distances requiring trillions of kilometers to describe. This was as revolutionary as Copernicus's discovery that Earth orbited the Sun, or Galileo's discovery that Jupiter had moons. But as these measurements accumulated, astronomers faced a practical problem. How do you communicate these enormous distances? Writing out 97 trillion kilometers gets tedious very quickly. Scientific papers were filled with huge numbers. Saying a star is at 657,000 astronomical units is awkward. Using multiples of the Sun's distance helped somewhat, but it still wasn't ideal. Someone, and history isn't entirely clear who first suggested it, proposed defining a new unit based directly on parallax geometry. The idea was beautifully simple and came naturally from the measurement technique itself. Take a right triangle. One side of the triangle, the base, is one astronomical unit, the distance from Earth to the Sun. The angle opposite that base, at the vertex where the star sits, is 1 arcsecond. Now solve for the length of the long side of the triangle, the hypotenuse, which is the distance to the star. Using basic trigonometry, specifically the tangent function, this distance works out to approximately 206,265 astronomical units. In more familiar terms, that's about 30.9 trillion kilometers, or about 19.2 trillion miles. They called this distance the parsec, a contraction of parallax and arcsecond. The name itself tells you exactly how it's defined. Here's the crucial thing to understand. 1 arcsecond was chosen because it's a round number in the angular measurement system humans invented thousands of years ago. The Babylonians, around 2000 BCE, developed a base 60 number system. They divided circles into 360 degrees because 360 has many factors. It's divisible by 2, 3, 4, 5, 6, 8, 9, 10, 12, and more. This makes it easy to divide circles into halves, thirds, quarters, and so on. They divided degrees into 60 arcminutes, because 60 is also highly divisible. And they divided arcminutes into 60 arcseconds for the same reason. This sexagesimal system, based on the number 60, is why we still measure time in 60-second minutes and 60-minute hours. The Babylonians invented it. The Greeks adopted it, and it spread throughout the ancient world and persisted to today. But there's nothing physically special about this choice. It's pure mathematical convenience based on ancient numbering preferences. An alien civilization using a different angular system might divide circles into some other number of degrees and define their angular units differently. The parsec is a consequence of human choices about how to measure angles, not anything fundamental about the universe. And virtually no star sits exactly 1 parsec from Earth. Our nearest stellar neighbor, Proxima Centauri, is about 1.302 parsecs away, according to the latest Gaia satellite measurements. That's the most accurate distance we have, measured to 4 significant figures. The bright star Sirius, prominent in winter skies, is about 2.64 parsecs. Vega, one of the brightest stars in summer skies, is about 7.7 parsecs. Bessel 61 Cygni is about 1.03 parsecs. The parsec doesn't mark any natural cosmic boundary. It's not the distance at which any particular physical process occurs. Stars don't start behaving differently at 1 parsec. There's no sphere of special significance at that distance. It's simply the distance that makes parallax arithmetic convenient, defined by an arbitrary angular choice. But that convenience turned out to be enormous for working astronomers. For astronomers doing parallax measurements every single day, the parsec had one massive advantage over any other distance unit. Measure a star's parallax in arcseconds, and its distance in parsecs is just 1 divided by that number. The relationship is direct and transparent. If a star shows a parallax of 0.5 arcseconds, it's 2 parsecs away. 0.25 arcseconds, 4 parsecs. 0.1 arcseconds, 10 parsecs. 0.05 arcseconds, 20 parsecs. Mental arithmetic, no calculator needed, no complex conversions, no looking up tables. Just invert the parallax and you have the distance. When you're processing hundreds or thousands of measurements by hand, which is what astronomers did before computers, this directness is invaluable. Imagine you're working through a notebook full of parallax measurements. Star A, 0.15 arcseconds. That's 6.67 parsecs. Star B, 0.28 arcseconds. That's 3.57 parsecs. Star C, 0.08 arcseconds. That's 12.5 parsecs. You can do this math in your head while working through the observations. The relationship is transparent. If you measure a parallax of 0.05 arcseconds, you instantly know the distance is 20 parsecs. If you make a mistake somewhere and accidentally get 0.5 arcseconds instead, the distance comes out to 2 parsecs, and you immediately know something went wrong, because that would make the star one of the very nearest in the sky, which should have been obvious from its brightness and other properties. Using kilometers or miles would require multiplying by large conversion factors every single time. Using astronomical units would require dividing by 206,000 every time. Using light years would require multiplying by about 3.26 every time. Each calculation is an opportunity for arithmetic errors. The parsec eliminates that. By the late 1800s, astronomers had measured parallaxes for dozens of stars. Each measurement confirmed that stars were scattered at enormous distances, far beyond anything in the solar system. The parallax technique was working. Distances were being measured reliably. The parsec became the natural unit for expressing those distances. It wasn't an official decision by any committee or scientific organization. It happened organically because it was genuinely useful. Astronomers started using it in papers because it simplified their work. Other astronomers reading those papers adopted it because it made the results easier to understand. Catalogs started listing distances in parsecs. Textbooks explained the concept. By 1900, it had become the default unit for stellar distances in professional astronomy. As telescope technology improved and observations reached deeper into space, astronomers needed larger multiples of the parsec. By the early 1900s, they were measuring distances to star clusters hundreds or thousands of parsecs away. Writing out 3,000 parsecs repeatedly was tedious, so they borrowed the metric system's prefixes and invented the kiloparsec, meaning 1,000 parsecs. A typical globular cluster, a spherical collection of hundreds of thousands of old stars, might be 15 kiloparsecs away. The center of our Milky Way galaxy is about 8.2 kiloparsecs from Earth. Then, in the 1920s, Edwin Hubble made one of astronomy's greatest discoveries. Those fuzzy spiral nebulae that astronomers had been cataloging for decades weren't gas clouds within our galaxy. They were separate galaxies, island universes containing billions of stars located at staggering distances. Hubble's discovery came from observing Cepheid variable stars in the Andromeda Nebula. Using the 100-inch telescope on Mount Wilson, at the time the largest telescope in the world, he could resolve individual stars in Andromeda. Some of these stars were Cepheid variables, which pulsate with regular periods. Henrietta Leavitt's period luminosity relationship, discovered in 1912, said that Cepheids with longer pulsation periods are intrinsically brighter. Hubble measured the periods of Cepheids in Andromeda, determined their true luminosities compared to how bright they appeared from Earth, and calculated the distance. The answer came out to about 280 kiloparsecs. Modern measurements give 780 kiloparsecs, so Hubble's initial distance was too small by a factor of nearly 3. But it was still clearly far beyond the Milky Way's boundaries. The Andromeda Galaxy, the nearest large spiral galaxy to the Milky Way, is about 780 kiloparsecs away. That's 780,000 parsecs. Writing that number repeatedly was tedious, so astronomers invented the megaparsec, meaning 1 million parsecs. Andromeda is 0.78 megaparsecs away. Other galaxies turned out to be even farther. The Virgo cluster of galaxies is about 16 megaparsecs away. The Coma cluster is about 100 megaparsecs. The expansion of the universe was carrying distant galaxies away from us at speeds proportional to their distance. Hubble discovered this relationship in 1929, and it revolutionized our understanding of the cosmos. As observations pushed even deeper into the cosmos, revealing the large-scale structure of the universe itself, the gigaparsec emerged. That's 1 billion parsecs. Distant galaxy clusters sit at distances measured in hundreds or thousands of megaparsecs. The edge of the observable universe, the farthest distance from which light has had time to reach us since the Big Bang, is about 14 gigaparsecs in comoving coordinates. We took a unit, originally based on a convenient, angular measurement for nearby stars, and kept multiplying it by thousands because the universe kept getting bigger in our observations. At each stage, the parsec stuck around, simply because converting everything to a new unit would have been more work than just adding a prefix. The infrastructure was already built around parsecs. All the formulas, all the catalogues, all the mental habits of astronomers assumed parsecs. Switching would have required coordinated effort across the entire field for unclear benefit. Understanding why the parsec became absolutely foundational to modern astronomy requires understanding what happened in the early 20th century. This is when astronomy transformed from a science of individual observations by single astronomers to a science of massive systematic surveys producing huge datasets. The Harvard College Observatory, under the direction of Edward Pickering starting in 1877, undertook an ambitious project. They decided to photograph the entire sky, visible from both their Massachusetts location and from an observatory they set up in Arequipa, Peru, to cover the southern sky. Over several decades, working with relatively primitive photographic plates, they created over 500,000 photographs, each capturing thousands of stars. This was an unprecedented amount of data, more information than any previous astronomical project had generated. Pickering needed people to analyze it all. Examine each plate, measure star positions and brightnesses, classify stellar spectra. This was tedious, time-consuming work, requiring good eyesight, attention to detail, and some mathematical skill. Pickering hired a team of women to do this work. He called them computers because their job was to compute stellar properties from the photographic plates. These women, despite being paid far less than male astronomers and often receiving no formal credit for their work, made some of astronomy's most important discoveries. Annie Jump Cannon classified over 350,000 stellar spectra, developing the classification system still used today. She could classify 3 stars per minute at her peak, and was the most prolific classifier in history. Williamina Fleming discovered over 300 variable stars and 10 novae. Cecilia Payne-Gaposchkin showed that stars are made primarily of hydrogen and helium, not the heavier elements found in Earth. But for our story, the most important of the Harvard computers was Henrietta Swan Leavitt. She was analyzing variable stars in the Magellanic Clouds, 2 small satellite galaxies visible from the southern hemisphere. Variable stars are stars whose brightness changes over time. Some vary randomly, flaring up and dimming unpredictably. But others pulsate with regular periods, getting brighter and dimmer in a repeating cycle. Leavitt was studying a particular type called Cepheid variables, named after the star Delta Cephei, which pulsates with a period of about 5 days. In 1912, after years of patient work measuring Cepheid periods and brightnesses, Leavitt made a revolutionary discovery. She found that Cepheid variables' pulsation periods directly relate to their intrinsic luminosity. Longer period Cepheids are genuinely brighter stars. A Cepheid that pulsates with a 30-day period is intrinsically brighter than one with a 10-day period, which is brighter than one with a 3-day period. The relationship is tight, predictable, and quantifiable. This changed everything for distance measurements. If you observe a Cepheid variable anywhere in the universe, measure its pulsation period, you immediately know its true intrinsic brightness. Compare that to how bright it appears from Earth, and you can calculate how far away it is using the inverse square law. Light spreads out as it travels, so brightness falls off as the square of distance. If something appears 4 times dimmer than expected, it must be twice as far away. This is exactly like seeing a light bulb in the distance. If you know it's a 100-watt bulb, you can judge distance by how dim it appears. A 100-watt bulb seen from 10 meters away appears much brighter than the same bulb seen from 100 meters away. Cepheids became astronomy's standard candles, objects whose true brightness is known, letting you measure distance by comparing true to apparent brightness. The crucial detail is that Cepheids are genuinely luminous stars. A typical Cepheid shines with the light of thousands of suns. They're bright enough to be seen in other galaxies, even millions of parsecs away. This let astronomers measure distances far beyond the reach of parallax. Parallax only works for nearby stars. With early 20th century technology, parallax was reliable out to maybe a few hundred parsecs for the brightest stars. For most stars, much less. Ground-based telescopes looking through Earth's turbulent atmosphere couldn't measure the tiny angles needed for more distant objects. Cepheids extended distance measurements to millions of parsecs, thousands of times farther than parallax could reach. But here's the key point for understanding the parsec's dominance. To calibrate the Cepheid period luminosity relationship, you need to know the actual distances to some Cepheids. You need to establish exactly how much brighter a 30-day Cepheid is than a 10-day Cepheid. The only way to measure those distances was parallax for the nearest Cepheids, or statistical parallax methods that average over many stars. The entire cosmic distance ladder, all the techniques that let us measure distances to far galaxies and determine the universe's scale, all of it traces back to those original parallax measurements. Parallax gives distances to nearby stars in parsecs. Those parsecs calibrate the Cepheid relationship. Cepheids give distances to galaxies in megaparsecs. Galaxies calibrate type Ia supernovae. Supernovae extend to gigaparsecs. Every step builds on the previous one. And every measurement comes out in parsecs, because that's what parallax naturally produces. So the parsec didn't just become standard for nearby stars, it became the foundation for all astronomical distance measurements. Every subsequent technique was calibrated using parsec distances. The unit spread through astronomy, not just because it was convenient for parallax work, but because parallax was the bedrock everything else stood on. While professional astronomers embraced the parsec universally across all subdisciplines, popular science went a completely different direction. The space race of the 1950s and 60s ignited massive public interest in astronomy and space exploration. The Soviet Union launched Sputnik in 1957, the first artificial satellite. Yuri Gagarin became the first human in space in 1961. NASA's Apollo program culminated in the moon landing in 1969. Suddenly, millions of people wanted to learn about the cosmos. Popular books flooded the market. Magazine articles explained black holes and quasars. Television shows explored the planets. Museums built planetariums. All of this needed to communicate astronomical distances to general audiences, and they all use light years instead of parsecs. Carl Sagan's Cosmos television series, which aired in 1980 and was seen by over 600 million people worldwide across 60 countries, used light years exclusively. When Sagan talked about Alpha Centauri, he said it was 4.24 light years away. When he discussed the Milky Way's size, he said it was 100,000 light-years in diameter. When he mentioned distant galaxies, he gave their distances in millions or billions of light-years. Not once in 13 episodes did he use the word parsec. This made perfect sense for public communication. The light-year concept explains itself. Light is the fastest thing in the universe. Everyone knows that. A year is a time span everyone understands intuitively. So a light year is obviously a huge distance. The distance light travels in 1 year at its incredible speed. The name itself conveys the concept. It's intuitive and evocative. The parsec, in contrast, requires extensive explanation. You have to explain what parallax is and why we use it. You have to explain what an arcsecond is and where that angular unit comes from. You have to explain why astronomers chose that particular angle for their definition. You have to draw diagrams showing the geometry. Even after all that explanation, most people find it abstract and unintuitive. It doesn't connect to everyday experience the way a light year does. The light year also has poetic resonance. When you say Andromeda is 2.5 million light-years away, people immediately understand that we're seeing light that left Andromeda 2.5 million years ago. We're looking back in time. The photons striking our telescopes began their journey when our distant ancestors were just learning to make stone tools. That's evocative and meaningful. Saying Andromeda is 0.78 megaparsecs away doesn't have the same impact. It's accurate, and professional astronomers use it, but it doesn't resonate emotionally. It doesn't immediately connect to anything in human experience. So a split emerged that persists to this day. Professional astronomers use parsecs in their research. Every research paper, every professional catalogue, every technical discussion uses parsecs or kiloparsecs or megaparsecs. But popular science uses light years. Every news article, every documentary, every museum exhibit uses light years. Same astronomer, same galaxy, different number depending on the audience. An astronomer writing a paper for the Astrophysical Journal will say, "A galaxy is 300 megaparsecs away." That same astronomer, interviewed for a New York Times article about the same galaxy, will say it's about 980 million light-years away. They're the same distance, just expressed in different units for different audiences. This dual system creates some confusion. People reading popular astronomy books think in light years. Then, if they take an astronomy course or try to read research papers, suddenly everything is in parsecs. They have to learn the conversion factor, 3.26 light-years per parsec, and mentally convert while reading. It's a barrier to engagement with professional astronomy. But both communities have legitimate reasons for their choices. Astronomers keep using parsecs because it connects directly to their measurement techniques and because their entire infrastructure assumes parsec units. All their databases store distances in parsecs. All their software expects parsec inputs. All their formulas are written with parsecs. Switching would require changing millions of lines of code, reformatting countless databases, and rewriting textbooks. Popular science keeps using light years because audiences find them more understandable and because the name itself is evocative and memorable. Science communicators want to engage people's imaginations. Saying a star is 4 light-years away makes people think about light traveling for 4 years. That's interesting and thought-provoking. Saying the same star is 1.3 parsecs away just sounds technical and dry. The parsec's dominance in professional astronomy was reinforced and extended enormously by space missions in the late 20th and early 21st centuries. In 2013, the European Space Agency launched a satellite called Gaia with an extraordinarily ambitious goal: measure precise positions and distances for over 1 billion stars. That's roughly 1% of all the stars in our Milky Way galaxy. Gaia carries 2 telescopes that continuously scan the sky. As the satellite slowly rotates, each star passes through the field of view multiple times over the mission lifetime. The satellite measures each star's position with incredible precision, down to micro-arcseconds for the brightest stars. That's 1/1,000,000th of an arcsecond. To put this in perspective, this is equivalent to measuring the width of a human hair from 1,000 kilometers away, or measuring the size of a coin on the moon as seen from Earth. This level of precision lets Gaia detect parallax for stars much farther away than was ever possible before. Previous catalogues from ground-based observations reached maybe a few hundred parsecs reliably. Gaia extended reliable parallax measurements to several kiloparsecs for bright stars. By 2022, Gaia had released data on over 1.8 billion stars. This is the most comprehensive and precise map of our galactic neighborhood ever created. It includes distances, 3-dimensional positions, proper motions showing how stars move through space, brightness in multiple wavelength bands, colors, and spectroscopic data for many stars. This dataset has transformed essentially every branch of astronomy. Studies of stellar evolution use Gaia distances to create precise Hertzsprung-Russell diagrams. Studies of the Milky Way's structure use Gaia data to map spiral arms and measure the galaxy's rotation. Studies of star formation use Gaia to identify young stellar clusters and trace how stars emerge from molecular clouds. Studies of galactic dynamics use Gaia proper motions to understand how the galaxy evolves. Exoplanet studies use Gaia parallaxes to determine precise planet radii and densities. Almost every astronomical paper published since 2022 cites Gaia data somewhere, and every single distance in the Gaia catalogue is reported in parsecs. This wasn't just traditional convention, it was the natural choice because Gaia fundamentally measures parallax. The satellite's primary output is parallax measurements in arcseconds. Each star has a measured parallax, an uncertainty in that parallax, and flags indicating the reliability of the measurement. Converting those parallaxes to distances in parsecs is trivial, just 1 divided by the parallax in arcseconds. Converting to any other unit requires additional steps and additional opportunities for errors. More importantly, Gaia was a multi-billion-dollar mission developed over 2 decades by hundreds of scientists and engineers across Europe. The entire data processing pipeline, all the software that reduces raw satellite measurements to final catalog values, all the analysis tools that astronomers use to work with the data, everything was built around parsecs from the start. This mission alone has probably ensured the parsec's dominance for at least another 50 years. Too much infrastructure now depends on it. Too many people have learned to think in parsecs. Too many tools assume parsec inputs. Switching would require massive, coordinated effort across the global astronomy community. Gaia's precision also revealed something interesting about the parsec definition itself. The simple geometric definition that Bessel would recognize has evolved considerably. Modern parallax measurements must account for Earth's orbit not being perfectly circular, but slightly elliptical. They account for gravitational tugs from other planets, particularly Jupiter and Saturn, that shift Earth's position slightly. They account for the Moon, which causes Earth to wobble slightly, as the Earth-Moon system orbits their common center of mass. They even account for light bending due to the Sun's gravity, an effect Einstein predicted in his general theory of relativity. Starlight passing very close to the Sun's edge gets deflected by about 1.75 arcseconds. That's larger than the parallaxes Gaia measures, so it must be corrected. The relativistic deflection varies with how close the star appears to the Sun and changes throughout the year as Earth orbits. So the simple, straight-line geometry implied by the original parsec definition is actually an approximation. The modern parsec is defined more carefully, accounting for these effects. The International Astronomical Union formally updated the parsec definition in 2015 to include relativistic corrections, but the basic concept remains the same. 1 parsec is still fundamentally the distance at which 1 astronomical unit subtends 1 arcsecond, just with all the subtle corrections that modern precision requires. 1 parsec equals 3.2616 light-years. You can remember this as roughly 3¼ light-years if you don't need precision. Light leaving a star 1 parsec away takes about 3 years and 3 months to reach Earth. In more everyday units, a parsec is about 30.9 trillion kilometers, or 19.2 trillion miles. These numbers are genuinely difficult for human brains to comprehend. Our cognitive systems evolved to understand distances we can walk or throw rocks across, not distances requiring trillions of kilometers to describe. Let me give you some context to make this more concrete. Consider the Parker Solar Probe, NASA's mission to study the Sun's corona by flying closer to the Sun than any previous spacecraft. Launched in 2018, it uses multiple Venus flybys to gradually drop deeper into the Sun's gravity well. At its maximum speed during close approaches to the Sun, the Parker Solar Probe reaches about 192 kilometers per second. That's 119 miles per second. It's the fastest human-made object ever built, moving at about 0.06% of light speed. At this incredible speed, Crossing just one astronomical unit from Earth to the Sun takes about 9 days. Voyager 1, launched in 1977 and now in interstellar space, took 35 years to get 40 trillion kilometers from the Sun, which is only about 1.3 parsecs. At the Parker Solar Probe's peak speed, if it were heading to a star 1 parsec away instead of orbiting the Sun, the journey would take about 5,100 years. Proxima Centauri, our nearest stellar neighbor, at 1.302 parsecs, would take the Parker Solar Probe roughly 6,600 years to reach. Sirius, at 2.64 parsecs, would take about 13,500 years. Even Alpha Centauri A and B, which are closer than Sirius, would take over 6,000 years. These aren't abstract numbers. They're the brutal reality of cosmic distances versus our current technology. Even our fastest spacecraft, pushing the boundaries of what chemical rockets and gravity assists can achieve, would require thousands of years to reach even the nearest stars. This is why interstellar travel remains science fiction for now. The distances are simply too vast for any propulsion system we can currently build. Chemically propelled rockets are limited by the energy density of chemical bonds. Nuclear rockets could do better, maybe reaching a few percent of light speed, reducing the trip to Proxima Centauri to perhaps 100 years instead of thousands. Theoretical concepts like nuclear pulse propulsion, detonating nuclear weapons behind a spacecraft and riding the shock wave, might reach 10% of light speed. Laser-pushed light sails, using powerful lasers to accelerate tiny probes, might reach 20% of light speed. But all of these are theoretical. Nobody's actually built them. And even at 20% of light speed, Proxima Centauri is still over 20 years away. Unless we develop fundamentally new physics, perhaps something like an Alcubierre warp drive that somehow gets around relativity's cosmic speed limit, practical interstellar travel with human crews remains far beyond our capabilities. We can barely get to Mars, and that's only 0.00003 parsecs away. Let me now explain why the parsec matters so much for actual astronomical research beyond just being a convenient unit. One of the most important tools in stellar astrophysics is something called the Hertzsprung-Russell diagram. This is a plot that shows stars' temperatures, usually expressed as spectral type or color, on one axis, and their luminosities, their true power output, on the other axis. When you plot thousands of stars on this diagram, clear patterns emerge. Most stars fall along a diagonal band running from hot bright stars in the upper left to cool dim stars in the lower right. This is called the main sequence, and it represents stars fusing hydrogen into helium in their cores. Giants cluster in a region toward the upper right. These are evolved stars that have exhausted their core hydrogen and expanded to enormous sizes. White dwarfs cluster in the lower left, hot but dim because they're so small. These patterns reveal how stars evolve over their lifetimes. A star, like the Sun, starts on the main sequence, gradually brightens as it ages, eventually runs out of core hydrogen and becomes a red giant, then sheds its outer layers and becomes a white dwarf. Massive stars follow a different path, becoming supergiants and eventually exploding as supernovae. But to create an accurate Hertzsprung-Russell diagram, you need to know stars' true luminosities, their actual power output. What you observe from Earth is apparent brightness, how bright the star looks to you. But apparent brightness depends on both the star's true luminosity and its distance. A dim star nearby can appear just as bright as a luminous star far away, just like a candle held close to your eye can appear as bright as a distant searchlight. To convert apparent brightness to true luminosity, you absolutely need distance. And here's where the parsec shows its utility in a way that other units don't. Astronomers define something called absolute magnitude as how bright a star would appear if placed at exactly 10 parsecs distance. This standardizes all comparisons. Every star's absolute magnitude tells you its true luminosity on an equal footing, as if all stars were lined up at the same distance. The conversion formula is simple when using parsecs. Absolute magnitude equals apparent magnitude minus 5 times the logarithm base 10 of distance in parsecs, plus 5. That plus 5 at the end comes from the reference distance being 10 parsecs. If you want to use any other distance unit, you have to add messier conversion factors into the formula, making it longer and more prone to arithmetic errors. For example, if you wanted to use light years, the formula becomes absolute magnitude equals apparent magnitude minus 5 times the logarithm of distance in light years divided by 32.6, which is 10 parsecs in light years. That division by 32.6 is awkward and makes the arithmetic harder. This might seem like a small thing, but when you're doing thousands or millions of these calculations, as astronomers routinely do with large data sets, keeping everything in one consistent unit prevents countless errors. Switching between units mid-calculation is exactly how mistakes happen. You forget to convert somewhere, or you apply a conversion factor in the wrong direction, and suddenly your luminosities are wrong. Modern distance measurement doesn't rely on parallax alone. Instead, astronomers use multiple independent techniques that cross-check each other, building what's called the cosmic distance ladder. Each rung of the ladder reaches farther into space, but relies on calibration from the rungs below it. This redundancy provides crucial validation. If two independent methods give similar distances to the same object, we can be confident the answer is correct. The bottom rung is parallax. This gives direct geometric distances to nearby stars based purely on triangulation. No assumptions about stellar physics required. No models of how stars shine. Just pure geometry. You measure angles, you get distances. Parallax is absolutely reliable within its range, which with Gaia extends to several thousand parsecs for the brightest stars and a few hundred parsecs for typical stars. The second rung uses spectroscopic parallax, which, despite the name, has nothing to do with actual parallax. This is perhaps the worst named technique in astronomy. It should be called spectroscopic distance estimation, or something similar. The technique analyzes a star's spectrum in detail to determine what type of star it is. Hot massive stars have different spectral features than cool low-mass stars. By examining spectral lines, you can classify the star and estimate its intrinsic luminosity. Compared to apparent brightness and calculate distance. This works out to tens of thousands of parsecs. The third rung is Cepheid variables, using Henrietta Leavitt's period luminosity relationship that we discussed earlier. Measure the pulsation period, which you can do photometrically without needing spectra. Determine true luminosity from the period. Compare to apparent brightness. Calculate distance. Cepheids are bright enough to see in other galaxies with large telescopes, extending measurements to millions of parsecs. The fourth rung uses Type Ia supernovae. These are exploding white dwarf stars in binary systems. The white dwarf accretes matter from a companion until it exceeds about 1.4 solar masses, called the Chandrasekhar limit. At this mass, carbon fusion ignites explosively in the degenerate core, and the star detonates. Because all Type Ia supernovae reach roughly the same mass before exploding, they reach remarkably consistent peak brightnesses. When you see a Type Ia supernova in a distant galaxy, you know roughly how bright it truly was at maximum light. Compare to how bright it appears, and you can calculate distance. Type 1. A supernovae are extraordinarily luminous at peak, briefly outshining their entire host galaxy. They can be seen billions of parsecs away, extending measurements across a significant fraction of the observable universe. This is how we measured cosmic acceleration and discovered dark energy in the late 1990s. Two teams measured distances to distant supernovae, compared to their redshifts, and found the universe's expansion is accelerating. This discovery won the 2011 Nobel Prize in Physics. Each technique has uncertainties. Parallax measurements have observational errors from photon noise, atmospheric turbulence for ground-based telescopes, and systematic effects. Spectroscopic parallax relies on stellar models that might be imperfect. The Cepheid period luminosity relationship has some intrinsic scatter because not all Cepheids of the same period have exactly the same luminosity. Type Ia supernovae aren't perfectly uniform, with variations of 10 to 20%. These uncertainties compound as you climb higher up the ladder. A 10% error in Cepheid distances becomes a 10% error in anything calibrated using Cepheids. A 15% error in supernova distances affects cosmological parameters derived from supernovae. Managing these error budgets is one of the major challenges in observational cosmology. But by using multiple independent methods and checking for agreement, astronomers build confidence in their distance measurements. If Cepheids and surface brightness fluctuations both give the same distance to a galaxy within uncertainties, that's reassuring. If they disagree significantly, something's wrong, and more investigation is needed. Throughout this entire ladder, from first step to last, parsecs provide the consistent framework. Every technique outputs distances in parsecs or kiloparsecs or megaparsecs. Every calibration uses parsec distances. The whole system hangs together because everybody's using the same units. Converting to different units at each step would introduce additional opportunities for errors. One of the most important numbers in all of cosmology is something called the Hubble constant. This quantifies the rate at which the universe is expanding. In the 1920s, Edwin Hubble, using Cepheid variables to measure galaxy distances and spectroscopy to measure their recession velocities, discovered a remarkable relationship. Distant galaxies are receding from us, moving away as space itself expands, and the farther away they are, the faster they recede. The relationship is linear. Double the distance, double the recession velocity. The Hubble constant quantifies this relationship. Its value is somewhere around 67 to 74 kilometers per second per megaparsec, depending on which measurement method you trust. What this means is that for every megaparsec of distance, a galaxy's recession velocity increases by that many kilometers per second. A galaxy 1 megaparsec away recedes at about 70 kilometers per second. A galaxy 2 megaparsecs away recedes at about 140 kilometers per second. A galaxy 10 megaparsecs away recedes at about 700 kilometers per second. At large enough distances, recession velocities approach the speed of light. This isn't motion through space, but space itself expanding between us and the galaxy. Recent measurements from different techniques disagree about the Hubble constant's exact value. And this disagreement is one of the biggest unsolved problems in cosmology. Observations of the cosmic microwave background, the afterglow of the Big Bang, analyzed using our best cosmological model with parameters from the Planck satellite, give a value around 67.4 kilometers per second. per megaparsec. But measurements using the cosmic distance ladder, starting with parallax to calibrate Cepheids and using Cepheids to calibrate type Ia supernovae, give a value around 73 kilometers per second per megaparsec. That's about an 8% disagreement. The two measurements have uncertainties of only about 2 or 3%, so they disagree at multiple sigma significance. This is genuinely worrying. Either one of the measurement techniques has a subtle systematic error nobody's found yet, or our standard cosmological model is missing something important. Maybe dark energy behaves differently than we think, changing its density over time. Maybe there's some unknown physics affecting cosmic expansion. Maybe neutrinos have slightly more mass than we thought. Maybe there's another particle we haven't discovered. This is called the Hubble tension, and resolving it is a major goal of observational cosmology. Notice the units of the Hubble constant: kilometers per second per megaparsec, velocity per distance. The parsec is baked into the fundamental equation describing how fast the universe is expanding. You could convert to other units. Some cosmologists use inverse gigayears, which has dimensions of inverse time, making the expansion rate look like a frequency. But most use kilometers per second per megaparsec because that's how we measure it. We measure galaxy recession velocities in kilometers per second from spectroscopic redshifts. We measure distances in megaparsecs using the distance ladder. So the natural units for the Hubble constant are kilometers per second per megaparsec. Using anything else requires conversions that don't add clarity. One elegant aspect of the parsec is how it connects different measurement scales across astronomy. At the foundation is the astronomical unit, the average distance from Earth to the Sun. This used to be measured through various ingenious techniques. In the 1800s, astronomers observed transits of Venus across the Sun's face from different locations on Earth. The parallax of Venus against the Sun gave Earth-Sun distance through triangulation. In the 20th century, radar ranging became possible. We bounce radio signals off planets like Venus and Mars, measure the round-trip time, multiply by the speed of light, and calculate distances with incredible precision. Modern measurements of the astronomical unit are accurate to within meters, out of 150 million kilometers. In 2012, the International Astronomical Union made a key decision about the astronomical unit. They redefined it as a fixed constant rather than a measured value. It's now defined as exactly 149,597,870.7 kilometers. Not approximately, but exactly. This makes the AU a defined unit, similar to how the meter is defined in terms of the speed of light traveling a certain distance in vacuum. We measure galaxy recession velocities in kilometers per second from spectroscopic redshifts. We measure distances in megaparsecs using the distance ladder. So the natural units for the Hubble constant are kilometers per second per megaparsec. Using anything else requires conversions that don't add clarity. One elegant aspect of the parsec is how it connects different measurement scales across astronomy. At the foundation is the astronomical unit, the average distance from Earth to the Sun. This used to be measured through various ingenious techniques. In the 1800s, astronomers observed transits of Venus across the Sun's face from different locations on Earth. The parallax of Venus against the Sun gave Earth-Sun distance through triangulation. In the 20th century, radar ranging became possible. We bounce radio signals off planets like Venus and Mars, measure the round-trip time, multiply by the speed of light, and calculate distances with incredible precision. Modern measurements of the astronomical unit are accurate to within meters out of 150 million kilometers. In 2012, the International Astronomical Union made a key decision about the astronomical unit. They redefined it as a fixed constant rather than a measured value. It's now defined as exactly 149,597,870.7 kilometers, not approximately, but exactly. This makes the AU a defined unit, similar to how the meter is defined in terms of the speed of light traveling a certain distance in vacuum. The parsec builds directly on the AU through its geometric definition. 1 parsec equals exactly 206,264.80624.7 astronomical units. Since the AU is now a defined constant, the parsec is also a defined constant. Its length is exactly 30.856775815 trillion kilometers, not a measured value anymore, but a fixed definition. Light speed connects parsecs to light years through another defined constant. The speed of light in vacuum is defined as exactly 299,792,458 meters per second. A light year is exactly how far light travels in 1 Julian year of 365.25 days, which works out to exactly 9.46073 trillion kilometers. Using these definitions, 1 parsec equals exactly 3.26156378 light years, good to many decimal places. These connections allow powerful cross-checks. You can measure a distance via parallax, giving you parsecs. Convert to light years using the exact conversion factor. Independently measure light travel time if you're observing something with changing brightness or periodicity. The numbers should match within uncertainties. If they don't, something's wrong with one of your measurements. This kind of cross-validation is crucial in science. No measurement technique is perfect. All have systematic errors that might go unnoticed. By using multiple independent approaches and checking for consistency, we catch errors and build confidence in our results. For nearby objects within a few hundred parsecs, the simple parsec definition works beautifully. Space is approximately flat on these scales. Light travels in essentially straight lines. The geometric definition applies cleanly. But for objects millions or billions of parsecs away, reality gets complicated. Einstein's general theory of relativity, published in 1915 and 1916, showed that mass and energy curve space-time. Light doesn't travel in perfectly straight lines through space. It follows curved paths, called geodesics, following the geometry of space-time itself. Massive objects like galaxies and galaxy clusters create significant space-time curvature, bending the path of light passing nearby. Gravitational lensing provides dramatic evidence of this. Light from a distant quasar, a luminous active galactic nucleus passing very close to a massive galaxy along our line of sight, gets bent and deflected. Sometimes the bending is so strong that we see multiple images of the same quasar arranged in a ring or arc pattern around the lensing galaxy. These Einstein rings are beautiful, scientifically valuable for measuring galaxy masses, but they also demonstrate that light paths aren't straight. The simple parsec definition assumes flat space and straight light paths. Neither assumption holds when light from very distant objects passes through regions of significant space-time curvature. You can still define distances, but you need to specify what you mean more carefully. Distance in curved space-time is ambiguous. Different definitions give different answers. Cosmic expansion adds even more complexity. When you observe a distant galaxy billions of parsecs away, you're seeing light that left that galaxy billions of years ago. During the time that light traveled toward Earth, space itself was expanding. The galaxy has moved farther away during light's journey. The expansion stretched the wavelength of the light, creating the redshift we observe. So what exactly do we mean by the distance to that galaxy? Do we mean how far away it was when the light was emitted? That's look-back distance or light travel distance. Do we mean how far away it is right now, at this moment? That's proper distance. But it's not directly measurable because we can't see the galaxy as it is now. Do we mean its coordinate distance in a framework that expands with the universe? That's co-moving distance. Cosmologists actually use 3 different distance definitions that all legitimately deserve to be called distance, but give different numerical answers for the same object. Co-moving distance is the galaxy's separation from Earth in a coordinate system that expands along with the universe. Imagine a grid painted on space that stretches as space expands. Co-moving distance measures separation in that expanding grid. It's useful for describing the underlying geometry of the universe because it factors out expansion. Proper distance is what you'd measure if you could freeze the universe at a specific moment and lay meter sticks through space from here to the galaxy. For the current moment, this gives the galaxy's separation right now. But for distant galaxies, we can't actually measure this directly because we see them as they were in the past, not as they are now. We have to calculate proper distance using cosmological models. Light travel distance, also called look-back distance, is how far the light actually traveled to reach us, which directly relates to look-back time. If light traveled for 10 billion years, it covered about 3 billion parsecs, or 10 billion light-years. This is closest to what most people intuitively think of as distance, but it's less useful for cosmological calculations. For nearby objects within a few tens of megaparsecs, these 3 distances are essentially equal. The universe hasn't expanded significantly over the relatively short light travel time involved. But for very distant galaxies at redshifts greater than 1, they can differ by factors of 2 or more. A galaxy we see as it was 10 billion years ago might have a light travel distance of 10 billion light-years, but a current proper distance of perhaps 18 billion light-years because space has expanded so much. Astronomers often use co-moving distances when discussing large-scale structure because that removes the expansion effect and shows the underlying cosmic geometry more clearly. When mapping the distribution of galaxies across cosmic time, co-moving coordinates make patterns easier to see. But different subfields favor different conventions. And you always need to check which distance definition is being used in any particular paper or dataset. This has led some cosmologists to argue we should stop reporting distances for very distant objects and instead report redshifts directly. Redshift is what we actually measure from observations. When you observe a galaxy's spectrum, you see familiar patterns of absorption or emission lines from hydrogen, oxygen, and other elements. But these lines appear at longer wavelengths compared to laboratory measurements of the same transitions. This redshift comes primarily from cosmic expansion, stretching light waves as they travel. Measure a galaxy's spectrum, identify the spectral lines by their characteristic patterns, calculate how much they're shifted compared to their rest wavelengths, and you have the redshift. That's the raw, observable. It's what we can measure directly without any assumptions about cosmology or how distances relate to expansion. Converting redshift to distance requires plugging the redshift into models of cosmic expansion that depend on assumptions about the universe's matter density, dark energy properties, curvature, and expansion history. Different assumptions give different distances for the same redshift. A galaxy reported as 10 gigaparsecs distant in a 1990 paper might be listed as 11 gigaparsecs in a 2025 paper, not because we made new observations of that galaxy, but because we refined our cosmological parameters. Our best fit values for the Hubble constant, matter density, and dark energy density have changed. So our distance redshift conversion changed. The redshift itself hasn't changed. Only our interpretation has. This argument for reporting redshifts has genuine merit. Redshifts are model-independent observables. Distances require model-dependent interpretations. But the argument hasn't won the day. Most astronomers still prefer converting redshifts to distances and reporting distances in parsecs or megaparsecs, even for very distant objects that require significant cosmological modeling to interpret. The distances feel more intuitive and concrete than redshifts, even if they're actually more model-dependent. Saying a galaxy is 3 gigaparsecs away gives people a sense of how far it is in a way that saying it has a redshift of 0.7 doesn't. This preference for distance over redshift persists despite the theoretical arguments for preferring redshifts. The parsec also creates practical barriers when astronomers need to collaborate with physicists, engineers, or computer scientists from other fields. These fields overwhelmingly use SI units, the international system of units based on meters, kilograms, and seconds. Physicists think in meters. Engineers design in meters. Computer algorithms expect inputs in standard units. Every interface between astronomy and these other fields requires careful unit conversion. Every physical constant needs to exist in both SI and astronomical versions. Every dataset needs careful unit tracking. This creates inefficiency and opportunities for errors. Consider gravitational wave astronomy, one of the most exciting developments of the past decade. The LIGO and Virgo detectors measure ripples in space-time caused by colliding black holes or neutron stars. These detectors are sensitive enough to measure space-time distortions smaller than the width of a proton. When black holes collide billions of parsecs away, the gravitational waves that reach Earth compress and stretch space by about 1 part in 10 to the 21st power. This field brings together observational astronomers who study the electromagnetic counterparts of gravitational wave events, theoretical physicists who model the gravitational wave signals using general relativity, experimental physicists who operate the detectors, and computer scientists running massive data analysis algorithms, searching for signals in noisy data. Physicists modeling the gravitational wave signals work in SI units because the equations of general relativity are naturally expressed in meters and seconds. Their numerical simulations track black holes orbiting and merging, outputting gravitational wave amplitudes as functions of time. These calculations give distances in meters from the observed wave amplitude and frequency. But astronomers analyzing the host galaxies and electromagnetic counterparts expect distances in megaparsecs. When a neutron-star merger produces both gravitational waves and a gamma-ray burst, astronomers want to know what galaxy it occurred in and how far away that galaxy is. They think in megaparsecs because that's what their galaxy catalogs use. Every interface between astronomy and these other fields requires careful unit conversion. Every physical constant needs to exist in both SI and astronomical versions. Every dataset needs careful unit tracking. This creates inefficiency and opportunities for errors. Consider gravitational wave astronomy, one of the most exciting developments of the past decade. The LIGO and Virgo detectors measure ripples in spacetime caused by colliding black holes or neutron stars. These detectors are sensitive enough to measure space-time distortions smaller than the width of a proton. When black holes collide billions of parsecs away, the gravitational waves that reach Earth compress and stretch space by about 1 part in 10 to the 21st power. This field brings together observational astronomers who study the electromagnetic counterparts of gravitational wave events, theoretical physicists who model the gravitational wave signals using general relativity, experimental physicists who operate the detectors, and computer scientists running massive data analysis algorithms, searching for signals in noisy data. Physicists modeling the gravitational wave signals work in SI units because the equations of general relativity are naturally expressed in meters and seconds. Their numerical simulations track black holes orbiting and merging, outputting gravitational wave amplitudes as functions of time. These calculations give distances in meters from the observed wave amplitude and frequency. But astronomers analyzing the host galaxies and electromagnetic counterparts expect distances in megaparsecs. When a neutron-star merger produces both gravitational waves and a gamma-ray burst, astronomers want to know what galaxy it occurred in and how far away that galaxy is. They think in megaparsecs because that's what their galaxy catalogs use. Computer scientists building the data processing pipelines need to convert back and forth constantly. Gravitational wave amplitude gives distance in meters. Convert to megaparsecs for astronomical context. Galaxy redshift gives distance in megaparsecs. Convert to meters for gravitational wave analysis. Every conversion is a potential source of errors. Similar issues arise in planetary science, where distances within the solar system are often expressed in astronomical units, but sometimes in kilometers, depending on context. Mission design for space probes needs distances in kilometers because that's what navigation software expects. But orbital dynamics calculations sometimes use AU for convenience. In astrobiology, when discussing potentially habitable exoplanets, do you report distances in parsecs or light years? Scientific papers use parsecs. Popular articles use light years. Press releases need to include both. The most famous unit conversion error in space history was the Mars Climate Orbiter disaster in 1999. The spacecraft was lost because one piece of software developed by Lockheed Martin generated thrust data in pound-force seconds, an imperial unit. Another piece of software, developed by NASA, expected Newton seconds, an SI unit. Nobody caught the discrepancy during testing. The spacecraft's trajectory calculations were wrong by a factor of about 4.4. Instead of entering orbit safely, it passed too close to Mars and burned up in the atmosphere. $327 million lost to a unit conversion error. That's an extreme example, but it illustrates the real dangers of working with multiple unit systems. Every interface between systems is a potential failure point. The more unit conversions required, the more opportunities for errors. Computer scientists building the data processing pipelines need to convert back and forth constantly. Gravitational wave amplitude gives distance in meters. Convert to megaparsecs for astronomical context. Galaxy redshift gives distance in megaparsecs. Convert to meters for gravitational wave analysis. Every conversion is a potential source of errors. Similar issues arise in planetary science, where distances within the solar system are often expressed in astronomical units, but sometimes in kilometers, depending on context. Mission design for space probes needs distances in kilometers because that's what navigation software expects. But orbital dynamics calculations sometimes use AU for convenience. In astrobiology, When discussing potentially habitable exoplanets, do you report distances in parsecs or light years? Scientific papers use parsecs, popular articles use light years. Press releases need to include both. The most famous unit conversion error in space history was the Mars Climate Orbiter disaster in 1999. The spacecraft was lost because one piece of software developed by Lockheed Martin generated thrust data in pound force seconds, an imperial unit. Another piece of software developed by NASA expected Newton seconds, an SI unit. Nobody caught the discrepancy during testing. The spacecraft's trajectory calculations were wrong by a factor of about 4.4. Instead of entering orbit safely, it passed too close to Mars and burned up in the atmosphere. $327 million lost to a unit conversion error. That's an extreme example, but it illustrates the real dangers of working with multiple unit systems. Every interface between systems is a potential failure point. The more unit conversions required, the more opportunities for errors. Teaching the Parsec to students presents its own set of challenges that perpetuate the unit's use despite its unintuitive nature. To understand what a Parsec is and why it's defined the way it is, students need to grasp several prerequisite concepts. They need to understand arcseconds as angular measurements, which requires understanding degrees and how we subdivide them. They need to understand astronomical units and how we measure solar system distances. They need to grasp parallax geometry and basic trigonometry. For a student taking an introductory astronomy course to fulfill a general education requirement, this is substantial time investment. These students often struggle with spatial reasoning and visualizing geometric relationships. Drawing triangles with Earth's orbit as the base and distant stars as vertices doesn't come naturally to everyone. The concept of measuring tiny angular shifts and converting those to distances requires mathematical sophistication that not all students bring to an introductory course. That class time could instead cover topics students might find more immediately engaging and memorable. Exoplanets and the search for life beyond Earth. Black holes and what happens when you fall into one. The Big Bang and how we know the universe had a beginning. Stellar evolution and why the sun will eventually become a red giant. These topics don't require understanding specialized distance units. A student can learn about the discovery of planets around other stars without needing to know those stars' distances in parsecs versus light years. Light years are far more accessible for teaching. Students already understand what a year is. They know light is fast, the fastest thing in the universe. The concept of distance light travels in a year makes immediate intuitive sense. You can teach the scale of the universe using light years without needing extensive mathematical prerequisites. Say Alpha Centauri is 4.2 light years away, and students instantly grasp that it's far and that we're seeing it as it was 4 years ago. No geometric diagrams needed. But here's the educational dilemma. As long as professional research papers use parsecs, students planning careers in astronomy must learn them. They need to read research papers as undergraduates to prepare for graduate school. Those papers will report distances in parsecs or kiloparsecs or megaparsecs. The students need to understand what those numbers mean and how to work with them fluently. They need to develop intuition for whether a claimed distance makes sense given other properties of an object. So, introductory astronomy courses end up teaching both units. Light years for the general education students who won't continue in the field. Parsecs for the majors. And anyone planning to read professional astronomy literature. This dual instruction takes more time than teaching just one unit would require. It's inefficient but necessary given the professional-popular split in unit preference. Upper-level undergraduate courses and graduate courses teach exclusively in parsecs because that's what students will encounter in research. Every catalogue they consult, every paper they read, every talk they attend at conferences will use parsecs. Learning to think in parsecs becomes part of professional socialization, joining the community of astronomers. This educational system perpetuates the unit through generations. Professors learned parsecs in their training. They internalized the unit, developed intuition for it, came to think naturally in those terms. So they teach parsecs to their students, who become the next generation of professors teaching parsecs to their students. The cycle continues independently of whether parsecs are objectively the best choice. They're what the profession uses, so they're what gets taught. Several major observatories planned for the 2030s will shape astronomy for the next several decades, and all of them will further entrench the parsec through their data products and analysis software. The extremely large telescope, being built by the European Southern Observatory in Chile's Atacama Desert, will have a primary mirror 39 meters in diameter. That's over 128 feet. It will be the largest optical telescope in the world when completed. Construction costs exceed €1 billion. First light is expected around 2027. The ELT will study exoplanet atmospheres in unprecedented detail, potentially detecting biosignatures. It will observe the most distant galaxies in the universe, seeing them as they were when the universe was young. It will study dark matter and dark energy. It will track stars orbiting Sagittarius A star, the supermassive black hole at our galaxy's center. All of this science will produce distances in parsecs because that's what astronomers designing the instruments and planning the observations expect. The Nancy Grace Roman Space Telescope, formerly known as WFIRST, is NASA's next major space observatory after James Webb. Named after NASA's first chief astronomer, it's designed for wide-field surveys and will revolutionize studies of dark energy, exoplanets, through gravitational microlensing and galactic structure. Launch is currently planned for May 2027. Total mission cost will exceed $3.9 billion. Roman will survey huge areas of sky, cataloging billions of stars and galaxies. It will measure distances to nearby galaxies through Cepheid variables and Type Ia supernovae, refining measurements of the Hubble constant. It will map the three-dimensional distribution of dark matter through weak gravitational lensing. Every distance measurement will be in parsecs because that's what the data processing pipelines output and what astronomical databases expect. The Square Kilometre Array is an international radio telescope project that will eventually have collecting area of 1 square kilometre spread across thousands of individual antennas in Australia and South Africa. It will be the most sensitive radio telescope ever built by several orders of magnitude. The first phase, SKA Low in Australia, operating at low radio frequencies, and SKA Mid in South Africa at higher frequencies, should be operational in the early 2030s. SKA will study the cosmic dawn, the period when the first stars formed in the early universe. It will detect radio pulsars with exquisite timing precision, using them to search for gravitational waves. It will map neutral hydrogen across the universe, tracing cosmic structure evolution. It will search for radio technosignatures from advanced civilizations. All of these programs will involve distance measurements in parsecs. All of these observatories, according to current plans, will use parsecs for their primary data products. The science teams designing these instruments and planning observations are professional astronomers who think in parsecs. The data processing pipelines being developed assume parsec units as defaults. The archive systems being built will store distances in parsecs. These are multi-billion-dollar, multi-decade projects that will produce data for 50 years or more. Their design decisions will influence astronomy well into the second half of the 21st century. Simply through continued use in flagship missions, the parsec will remain entrenched. Each new catalog adds to the accumulation of parsecant-based data. Each new survey builds on previous surveys' distance scales. The infrastructure grows and hardens. Switching becomes progressively more difficult as more depends on the existing system. But countervailing forces exist that might eventually shift practice toward more accessible units. Astronomy is becoming increasingly data-driven and interdisciplinary. Modern surveys produce datasets so large that individual astronomers can't analyze them alone. Collaborations span many fields, bringing together experts in physics, statistics, computer science, machine learning, and domain-specific areas. If climate scientists want to use astronomical data to understand solar variability's effects on Earth's climate over geological timescales, they shouldn't need to learn specialized astronomical units first. The data should be accessible in familiar units. If geologists want to compare impact crater ages to supernova rates that might have caused extinction events, converting between parsecs and familiar distance units shouldn't be a barrier to entry. Open science movements emphasize making data accessible beyond the immediate research community that generated it. Data should be fair, findable, accessible, interoperable, and reusable. Requiring specialized unit knowledge to interpret data works against these goals. Parsecs are a barrier to interdisciplinary research, even if a small one. When we eventually detect biosignatures in an exoplanet's atmosphere confirming life beyond Earth, the distance to that planet will become one of the most discussed numbers in human history. Media coverage will be overwhelming. Every news outlet worldwide will report the discovery. Every person on Earth will hear about it. And they will almost certainly give the distance in light years, not parsecs, because that's what general audiences can understand. Imagine the headlines. Life found on planet 40 light years away resonates with people. They understand that light from that planet takes 40 years to reach Earth. They grasp the timescales involved. Life found on planet 12.3 parsecs away sounds technical and alienating. It requires explanation that most news articles won't provide. This might create pressure for astronomers to standardize on light years for public-facing work, or, at minimum, to always provide both units in press releases and papers intended for broad audiences. If every press release has to convert from parsecs to light years anyway for public comprehension, why not provide light years directly in the scientific papers as well? Similarly, if we ever reach the point of seriously planning interstellar missions, perhaps using breakthrough technologies like nuclear pulse propulsion, laser-pushed light sails, or fusion rockets, all discussion of those missions will naturally use light years. A mission to Alpha Centauri, 4.24 light-years away, immediately tells you that light-speed travel would take 4.24 years. The travel time and distance have obvious connections. At 10% of light speed, which might be achievable with advanced propulsion, the trip would take 42 years. At 20% of light speed, 21 years. These calculations are straightforward when using light years. With parsecs, you'd need to do conversions to understand timescales. Alpha Centauri at 1.3 parsecs requires mentally converting to light years before you can assess travel times at various speeds. The most likely future, in my assessment, is that parsecs remain dominant in professional astronomy for the foreseeable future, but software tools make the choice of units less important practically. Modern astronomical databases don't just store numbers. They store numbers with metadata indicating units, precision, measurement method, and provenance. Query a database for a galaxy's distance, specify what units you want in the output, and the system converts automatically. This capability already exists in many systems. The Simbad astronomical database, maintained by the Centre de Données Astronomiques de Strasbourg, stores distances primarily in parsecs but can display them in light years on request. The NASA Exoplanet Archive provides distances in both parsecs and light years by default. These are proofs of concept showing that multi-unit support is technically straightforward. This functionality just needs to become more universal and user-friendly. Every major astronomical database and analysis tool should support seamless unit conversion. Users should be able to set preferences once and have everything display in their preferred units automatically. No manual conversion required. Machine learning algorithms are increasingly used to analyze astronomical data, discovering patterns humans might miss. Adding intelligent unit conversion to these systems is straightforward. The algorithms don't care whether inputs are in parsecs, light years, or meters. They work with numbers. Humans care about units because we need to interpret the numbers. But software can handle conversions invisibly. Systems could learn individual users' preferences through usage patterns. If an astronomer always queries distances and immediately converts to parsecs, the system learns to provide parsecs by default for that user. If a science communicator always converts to light years, provide light years. If a physicist working on gravitational waves wants meters, provide meters. Adaptive interfaces that learn user preferences already exist in other contexts. Applying this to astronomical unit conversion is natural. This doesn't resolve the fundamental question of which unit is objectively better or more natural. Different communities will have different preferences based on their needs and training, but it makes the question less important in practice. The parsec can remain astronomy's native unit, while becoming less of a barrier to outsiders because translation will be seamless and automatic. The main blocker to changing units isn't technical capability. We have the technology to convert between units easily. The blocker is social and institutional. Individual astronomers have little incentive to deviate from standard practice. If you submit a paper reporting distances in light years or meters when everyone else uses parsecs, reviewers might flag it as non-standard. They might request you convert to parsecs before publication. Using non-standard units marks you as an outsider or someone who doesn't understand field conventions. Database managers might hesitate to ingest your data if it uses non-standard units. They'd need to verify the units are correctly flagged in metadata. They'd need to ensure conversion factors are applied correctly. It's easier to require standard units than to handle multiple possibilities. So databases often specify required units, and parsecs is what they require. This is a classic collective action problem from economics and sociology. Everyone might benefit if everyone switched to a more accessible or universal unit like light years or meters. But nobody wants to be the first to switch because doing so creates individual costs through friction with existing infrastructure and norms. The group would benefit from coordination, but individuals are punished for deviating unilaterally. There have been some attempts at coordination to address this. Some journals have discussed requiring papers to report distances in both parsecs and light years, giving professional and popular units simultaneously. This would make papers more accessible to broader audiences while still serving professional needs. But implementation has been inconsistent. Some journals adopted this recommendation, others didn't. Without universal adoption, the impact is limited. Some databases added options to output distances in multiple units on request. The Sloan Digital Sky Survey, one of the most comprehensive galaxy surveys ever conducted, provides distances in both parsecs and light years in many of its data products. The Gaia archive allows users to choose output units for many parameters. These are steps toward better accessibility, but these efforts have been piecemeal. They haven't fundamentally changed professional practice. Astronomers still write papers primarily in parsecs. They still think in parsecs when doing research. They still present conference talks using parsecs. The infrastructure accommodates alternatives in some places, but the default remains parsecs. The International Astronomical Union could theoretically mandate a change through an official resolution. They're the body that makes formal decisions about astronomical nomenclature, coordinate systems, time standards, and unit definitions. They could decree that all astronomical publications must report distances in both parsecs and light years, or that light years should become the primary unit with parsecs as secondary. But the IAU generally prefers letting practice evolve organically rather than imposing top-down changes. They recognize that mandating changes that the community isn't ready for breeds resentment and is likely to be ignored. Scientific communities are difficult to steer by fiat. Change works better when it emerges from consensus. And organically, practice hasn't evolved toward abandoning parsecs. If anything, Gaia has strengthened parsec dominance by producing a massive parsecant-based catalogue that everyone uses. The scientific literature continues to use parsecs almost exclusively. Conference talks use parsecs. Grant proposals use parsecs. The status quo persists. My prediction for 50 years from now is that the parsec remains the dominant unit in professional astronomy, but with significantly better software infrastructure, making the choice of units less constraining. Major surveys launching in the next decade, like the Vera Rubin Observatory's Legacy Survey of Space and Time, starting in 2025, will produce parsecant-based data. LSST will survey the entire visible sky every few nights for 10 years, cataloging billions of objects and tracking anything that changes. All distances will be in parsecs. That data will be analyzed and reanalyzed for decades. By mid-century, we'll have another generation of parsecant-based data accumulated on top of Gaia, on top of Sloan, on top of the hundreds of earlier surveys. The accumulated infrastructure of parsecant-based catalogues will be even larger and more entrenched than today. But simultaneously, better software infrastructure will make units more transparent to users. Data visualization tools will seamlessly convert between units. Analysis pipelines will accept inputs in any reasonable unit and convert as needed. Machine learning systems will learn user preferences. The parsec will remain astronomy's native unit, but become less of a barrier to entry because translation will be automatic and invisible. Young astronomers entering the field in 2075 will probably still learn parsecs as part of their training. Graduate programs will teach parsecs because that's what the literature uses. They'll use parsecs in their professional work, writing papers and giving talks. They'll barely question whether alternatives might be better because the infrastructure they inherit will be built around parsecs. But those same young astronomers will also have tools that previous generations lacked. They'll work with data systems that handle unit conversion transparently. They'll collaborate with researchers from other fields without unit barriers. They'll communicate with the public using light years without thinking about it. The parsec will be their professional language, but not an exclusive one. fields develop their specialized conventions and terminology for good reasons. These conventions encode accumulated wisdom and make communication within the field more efficient. Learning those conventions is part of joining the field and becoming fluent in its discourse. Particle physics has its electron volts for energy, barns for cross-sections, and inverse femtobarns for integrated luminosity. Nuclear physics has its becquerels for radioactivity and grays for absorbed radiation dose. Astronomy has its parsecs for distance. These specialized units often seem arbitrary to outsiders. Why measure energy in electron volts instead of joules? Why measure cross-sections in barns, where one barn equals 10 to the minus 28 square meters? The answers involve historical accident and practical convenience, similar to the parsec. But these units serve their communities well by making common calculations simpler and by creating shared language. The parsec emerged from Friedrich Wilhelm Bessel's landmark 1838 measurement of stellar parallax to 61 Cygni. It proved immediately useful for parallax work because of its geometric simplicity and direct relationship to measured angles. It became the standard unit across all of astronomy through a combination of genuine utility for working astronomers and historical momentum as the field grew. It persists today, despite recognized limitations, because changing would require coordinated effort across the entire global astronomy community. Databases would need updating. Software would need rewriting. Textbooks would need revising. Papers would need to be written differently. Astronomers would need to retrain their intuitions. The costs of change are substantial and concentrated on those doing the changing, while benefits are diffuse and uncertain. Fields develop their specialized conventions and terminology for good reasons. These conventions encode accumulated wisdom and make communication within the field more efficient. Learning those conventions is part of joining the field and becoming fluent in its discourse. Particle physics has its electron volts for energy, barns for cross-sections, and inverse femtobarns for integrated luminosity. Nuclear physics has its becquerels for radioactivity and grays for absorbed radiation dose. Astronomy has its parsecs for distance. These specialized units often seem arbitrary to outsiders. Why measure energy in electron volts instead of joules? Why measure cross-sections in barns, where one barn equals 10 to the minus 28 square meters? The answers involve historical accident and practical convenience, similar to the parsec. But these units serve their communities well by making common calculations simpler and by creating shared language. The parsec emerged from Friedrich Wilhelm Bessel's landmark 1838 measurement of stellar parallax to 61 Cygni. It proved immediately useful for parallax work because of its geometric simplicity and direct relationship to measured angles. It became the standard unit across all of astronomy through a combination of genuine utility for working astronomers and historical momentum as the field grew. It persists today despite recognized limitations because changing would require coordinated effort across the entire global astronomy community. Databases would need updating, software would need rewriting, textbooks would need revising, papers would need to be written differently. Astronomers would need to retrain their intuitions. The costs of change are substantial and concentrated on those doing the changing, while benefits are diffuse and uncertain. Is the parsec optimal? No. A unit based on human angular measurement conventions and marking no natural cosmic boundary is clearly arbitrary in deep ways. Is it good enough? Clearly, yes, since the field continues to function well and make rapid progress using it. Astronomy has never been more productive than it is today. And that productivity isn't limited by the choice of distance units. The Parsec story reveals how arbitrary choices, made for good reasons in particular contexts, can become entrenched standards that shape practice for centuries. It shows how historical momentum and infrastructure investment create resistance to change, even when alternatives might be better in some ways. It demonstrates how social factors matter as much as technical factors in determining scientific practice. This pattern appears everywhere in human endeavors, not just in science. Languages contain arbitrary grammatical features and irregular verbs that persist because changing requires coordinating millions of speakers. Technology standards like QWERTY keyboard layouts or the width of railroad tracks often reflect early design choices rather than optimal solutions discovered later. Legal systems carry historical precedents and procedural rules that made sense in past contexts but persist into changed circumstances. Academic institutions maintain tenure systems and departmental structures reflecting 19th century university organization. Every time you see an astronomical distance reported in parsecs, you're witnessing this process in action. You're seeing the echo of an 1838 measurement technique. You're seeing accumulated practice from nearly 2 centuries of astronomers, all using the same unit. You're seeing the peculiar path by which one particular angular choice became foundational to an entire scientific field. Behind every measurement, every scientific paper, every physical theory, there are humans making choices. Sometimes those choices are brilliant insights that transform understanding. Newton choosing to analyze forces and accelerations rather than speeds. Einstein choosing to make the speed of light constant and let time be relative. Hubble choosing to study Cepheids in nebulae to measure their distances. Sometimes choices are arbitrary decisions about conventions that happen to stick. The choice to divide circles into 360 degrees. The choice to define 1 arcsecond as 1/3600th of a degree. The choice to base a distance unit on 1 arcsecond of parallax. Sometimes, choices are just whatever turned out convenient at the time and never got seriously re-examined. Using parsecs because that's what parallax measurements naturally produce. Continuing with parsecs because that's what existing catalogs use. Teaching parsecs because that's what research papers report. The parsec is all three simultaneously. It was a clever choice for parallax work, elegant in its geometric simplicity. It was an arbitrary choice in that 1 arcsecond has no physical significance, just historical accident. And it was convenient enough that nobody saw sufficient reason to change once institutional infrastructure grew around it. When you look up at the night sky on a clear evening, those stars are separated by distances measured in parsecs by professional astronomers. Not because parsecs are the best possible unit by some objective measure, but because they're established and the costs of switching are high while benefits remain unclear. Proxima Centauri sits 1.302 parsecs away. Sirius sits 2.64 parsecs away. Betelgeuse sits somewhere around 170 parsecs away, though uncertainty remains. The galactic center sits about 8.2 kiloparsecs away. Andromeda sits 780 kiloparsecs away. These numbers tell stories of light traveling for years across incomprehensible emptiness. Stories of stellar birth in collapsing gas clouds, stellar evolution through nuclear fusion stages, and stellar death in planetary nebulae or supernova explosions. Stories of galaxies colliding over hundreds of millions of years, of supermassive black holes growing, of cosmic expansion carrying everything apart. And stories of humans trying to measure and understand it all, using whatever tools and units we developed along the way. The Parsec is one of those tools. Strange to outsiders, yes. Unintuitive to anyone not trained in astronomy, absolutely. But familiar and functional for those who use it every day. Science is ultimately a human endeavor, done by people working in communities with shared training, language, and practices. Social and psychological factors matter as much as pure physics or mathematics in determining how science gets done. Communities develop shared language and conventions that reinforce group identity and smooth collaboration within the group, even if those same conventions create barriers to outsiders. Maybe having field-specific traditions and units serves valuable purposes beyond pure efficiency. Maybe the Parsec, precisely because it requires explanation and training to understand, helps define who's part of the professional astronomy community. Maybe there's value in maintaining some specialized knowledge that marks expertise and signals membership in the community of practice. Understanding this makes us better, more sophisticated consumers of science. When we read that scientists disagree about something, or that different fields use different approaches to the same problem, we shouldn't always assume it's because the facts are uncertain or the scientists are confused. Sometimes it's because conventions differ across communities, standards vary between fields, or definitions aren't universal across all contexts. This doesn't mean science is arbitrary or unreliable. It means science is done by humans embedded in social structures with histories and traditions. Understanding this also gives us more realistic expectations about scientific progress and change. Progress doesn't happen just because someone has a better idea or because new evidence emerges that invalidates old theories. Change happens when communities collectively decide to adopt new practices, when institutions invest resources in new infrastructure, when enough people conclude that benefits of changing outweigh costs and that coordination problems can be solved. That's fundamentally a social process, not just a scientific or technical one. It involves persuasion and argument, coordination across many actors, political skill in building coalitions, and willingness to invest resources in transitions whose payoffs might not be immediate. The Parsec's persistence over nearly 2 centuries demonstrates how powerful these social and institutional factors can be in maintaining status quo. Thank you for spending these 2 hours exploring the strange story of the Parsec. If this changed how you think about scientific standards, about how science actually works as a human endeavor, about the ways history and social factors shape current practice, then the time was well spent. Keep looking up at those stars scattered across the night sky. They're not going anywhere, at least not on human timescales. And whether we measure their distances in parsecs, light years, astronomical units, meters, or some future unit we haven't invented yet, their light has traveled across the cosmos to reach us. That remains profound and worthy of wonder no matter what units we choose to describe it. Good night.